Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on fuzziness of measurement. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions that you may have in mind. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? Question number four, how to apply learned knowledge in this course? So let me start with the answer to this first question, which is about why to study this course. By now, you should know that our mission on Earth include number one, to understand the world through the discovery of the knowledge and to improve the world through the invention of a smart product, smart system, and the smart machine. Then how to discover knowledge? The answer is to use the sensory data. Then how to obtain sensory data? The answer is to make use of measurement and the sensing system. All right. Then how to invent smart products, smart machine, and the smart system? The answer is to incorporate closed-loop feedback control system into the design of these smart products, smart machine, and the smart system. Then what is a closed-loop feedback control system? The answer is it is a system with three basic building blocks or three basic building modules. One of them is a sensor, right? So therefore, this course is extremely important, all right? And this slide also showing you that in future, you may see the presence of smart street lighting system, smart parking system, smart building system, smart home system, smart environmental system, smart healthcare system, and the Internet of Things in city, all right? Then what is the Internet of Things? Basically, it's a network with the sensor and the network with the actuator. Then you see the presence of a sensor inside Internet of Things. The second question is about how to study this course. My advice to you is to put yourself into the mindset of a designer. Then in this way, with the keyword of a design or designer, automatically you will ask yourself about these four questions. Who are the user? What are the needs of this user? What are the functionality of the product or system that you are going to develop in order to meet the need of this user? And what should be the solution behind the design of your product or your system in terms of sensor or Internet of a sensor, all right? So answer to question number one should be obvious to you because the user include ourselves and the smart product, smart machine, and the smart system, all right? So answer to question number two should be also obvious to you because this user has a common need, which is to have sensory data, all right? So answer to question number three depends on the nature of specific user. For example, a smart vehicle may need to have a certain type of a sensor, and the smart robot may need to have another type of a sensor, all right? Then answer to question number four is to study well this course. At the end of the study of this course, you will know the basic principle behind the design of your future sensor or your future Internet of a sensor, etc. All right. Then the question number three is about what are you going to study from this course. Basically, this course covers the study of the physical principle behind the design of a popular sensor in electric domain, in magnetic domain, in environmental system, and in intelligence system. In addition, this course also covers the basic knowledge about the physical world, the basic knowledge about the conceptual world, and also this course will teach you the basic detail for you to cope with randomness in the physical world and for you to understand the phenomenon of fuzziness in conceptual world. All right. And by now, more or less we have already complete the study of the physical principle behind the design of engineering sensor. Then the remaining 2 lectures is about the fuzziness and the conceptual world, all right? And these 2 lectures basically is for you to understand how to transform engineering sensor into human-like sensory system, all right? And you understand our sensory system are not crisp. For example, our skin is not able to tell you the exact value of a temperature. However, we are able to describe the situation about the temperature with human language, right? So that is an advantage, for having a human-like sensory system. This is because such transformation of crisp sensory data into fuzzy sensory belief, help human being to compress, the amount of data so that our small brain could store a lot of knowledge about the huge physical world. Because the physical world is huge, our brain is small. Then how to store such a huge amount of knowledge inside our small brain? Answer is what? To make use of a human language to describe the knowledge in the physical world. In this way, automatically we achieve the important result of knowledge compression. All right, so it's a magic, property of humans' sensory system. So therefore, it is important for us to know how to transform engineering sensor into human-like sensor, right? So it's very, very interesting topics for you to know, and eventually, based on the basic detail or basic knowledge about fuzziness, conceptual world, then you will be motivated to further the study with the course of machine intelligence or artificial intelligence in future, right? How to apply learned knowledge from this course. So basically, we hope that you should be able to apply learned knowledge in order to guide the design of a sensor or measurement and the sensing system. All right, and this slide basically showing you the guideline. All right, so the design of a sensor involves 2 steps. Step number 1 is to transform the value of the physical quantity on the measurement into readable value. And the step number 2 is to calibrate the sensor or measurement and the sensing system so that the output will be exactly equal to the input, and the unit of the measurement associated to the output will be the same as the unit of the measurement of the physical quantity on the measurement. All right. And for step number 1, basically you may face 2 situations. The first situation corresponds to the case in which it is good enough for you to just make use of a front-end sensing element in order to transform the value of the physical quantity on the measurement into readable value. However, in most cases, you may face the situation in which you have to make use of a series of at least 2 sensing element in order to transform the value of a physical quantity on the measurement into readable value. So as long as you follow the guideline, outline in this slide, then you should be able to apply learned knowledge, in order to come out with the design of your future sensor or your future Internet of Sensor, etc. All right, so now we are ready to start to study, today's lecture on fuzziness involved in the measurement. All right, and fuzzy logic, you understand, is a course which requires at least 1 semester of study, and therefore I'm trying to compress this course into 1 hour of the lecture. Then in this way, you will understand the basic detail or basic knowledge about the phenomenon of fuzziness, and then we learn the knowledge from this lecture, and eventually you should be able to transform engineering sensor into human-like sensor. And as I mentioned just now, okay, human-like sensor has a very, very impressive capability to adapt to the variation of sensory data. All right, so this is a very important capability of a human intelligence, right? So if we make our mental activity consistent, all right, on one hand, and also make our mental system to handle large amount of knowledge from the physical world, all right? Because with the use of the fuzziness, the phenomenon of fuzziness, so actually our mind achieve automatically knowledge compression, all right? So, and traditionally, fuzzy logic is not taught from the angle of AI, okay? Especially the causality behind the development of a fuzzy logic is not clear, right? So the common belief is about the statement which says that the fuzzy logic basically is the extension of binary logic. So you know binary logic, we only play with the 0, 1. All right, then how's about the value between 0, 1, right? Then we come out the logic with infinity number of value between 0, 1. Then we name it as a fuzzy logic, right? So actually, if you look at the nature, especially look at the human intelligence, the motivation actually is not to have logic with value between 0, 1. Okay, so actually is a knowledge compression, all right? So in this way, we can achieve one-to-many association. Let's say one belief or one knowledge may correspond to many, many instances of sensory data, right? So no need to have a description for each individual sensory data, right? So like this way, we achieve a data compression. And also, the phenomenon of fuzzy logic is related to the belief, because in the textbook, people say that fuzzy logic is a study which handles the vagueness. I believe this is wrong, right? Because later on you will see the statement. Let's say today or this room is warm. If let's look at this statement is very clear. There's no vagueness, China. The room is warm. Okay, everyone know. Because vagueness means what is lack of knowledge, so people cannot understand it. For example, when you write the paper, write the report, if your supervisor tell you inside your report, all the description are very, very vague. Okay, no people can understand what you have written inside your report. That is a vagueness. Vagueness means what? There's a lack of knowledge, lack of information. All right. So fuzziness is not vagueness. Okay. So fuzziness is about belief. All right. So it's related to belief. So I try to introduce, okay, fuzzy logic or the fuzziness from the point of view of human sensory behavior. Then we will have a strong motivation to adopt, okay, or make use of the phenomenon of fuzziness, okay, to venture into the AI and venture into the design of a fuzzy controller or fuzzy decision maker. All right, so you see, I will start with the belief set. All right, so that gives you a very convincing, okay, motivation to understand what is the true nature of fuzziness in the conceptual world. Because the last lecture we talk about what is a conceptual world, right? Okay. Then after that, I will just telling you some detail about the fuzzy control, all right? And here we do not have time to tell you about the application of fuzziness in artificial intelligence, because we have another course which is called machine intelligence. So I'm not going to overlap with that course. All right. Okay. So let's start with belief set. All right. So it's like for human sensory system, basically it will trigger belief. Once you enter the room, then you will believe this room is dark, this room is warm, or this room is bright, this room is cool, or this room is small, this room is big, right? But all your belief, there's no vagueness at all, it's very consistent, all right, very clear. Okay, the room is dark, all right? The room is white, there's no vagueness at all. But there's a belief, because based on our eyes, sensory data, okay, I believe this room is large with a certain confidence level or certain level of a possibility for people to have a similar belief, right? And when you enter the room, your skin will tell you the temperature, the humidity inside the room. Then that will trigger the belief also in your mind, all right? So that belief is not vague at all. It's very clear. This room is cool, all right? And there is a certain level of possibility for others to have a similar belief. Then you see fuzziness is linked to possibility. And you remember our first lecture, second lecture, I talk about the randomness in the physical world. Randomness is related to probability, all right? So theoretically, the study of fuzzy logic should be under the name of a possibility, right? So it is like when we study the randomness. Randomness basically is a phenomenon of a competition, compete for occurrence, right? Then the textbook title normally is probability and the statistic, right? So very, very academic term, all right? Then for fuzzy logic, the more academic term should be possibility, okay? What is the possibility for this sensory data to trigger this belief and trigger that belief? That should be the nature of humans' intelligence with our own sensory input, right? So when we enter the room, immediately we know whether it is large, it is small, it is cool, it is warm, or it is humid, or it is cloudy, or it is empty or not, all right? So it is very interesting, all right? And the belief set is very, very important, because when people use the term vagueness and the membership function, actually they miss out this opportunity of solving this very, very important or long-lasting problem in AI. That is a simple grounding problem. And I believe we are the first one in the world bring the solution to this long-lasting problem in AI, and without spending a single cent from any research project. Okay, purely by doing teaching, then we discover a very, very important breakthrough in a very, very important discipline. You see, magic, John, right? So simple grounding problem is a long-lasting problem in artificial intelligence. This problem consists of finding solution which allow us or allow any machine to transform meaningful signal into meaningful symbol in human language. That's it. All right. Then we discover the solution should be the positive possibility function. That's it. All right. Then in general, we can use normalize the Gaussian function to serve as a possibility function, or use a trapezoid function to serve as a possibility function, or simply make use of a triangle function to serve as a possibility function, right? So because many human experience could be described with one of these functions, right? And eventually for decision making, action taking, okay? So these three possibility function should be good enough, but later on you will see, right? So, so this is a very, very interesting application with belief set. And later on you will see with the fuzzy set allow machine to imitate humans' experience. For example, we have a human expert. Human expert could describe his or her experience with the possibility function. For example, if this kinds of sensory data may trigger this type of a belief, with a certain level of a possibility, then how to determine the value of a possibility. Then these three functions are the most popular one. They should be good enough to cover majority of cases with human experts experience, right? So this is an application which will motivate us to pay attention, to the usefulness of a belief set, right? So, and in this slide I mentioned, simple grounding problem in AI is the problem which consists of a finding solution for transformation from a meaningful signal to meaningful symbol in human language. Therefore, then we need to know what is the human language, what is the nature of the human language. So actually, this answer another important question in AI, knowledge representation. If you check the textbook in AI, and you will find out that one of the major issues in AI is the knowledge representation. So actually, every one of us know the solution to that major issue. The best way to represent language, or the best way to represent knowledge, is the use of the human language. Now you can link these together, transform a signal, meaningful signal into meaningful symbol in human language. This is a part of the process of representing knowledge with the use of human language. Then we need to know what is a human language. So actually, human language include a natural language, programming language, and the technical language, all right? So we will discuss this more in detail in the last lecture about the study of conceptual world. And here you just remember this nature is good enough. So language basically is the best tool for us to represent knowledge or encode knowledge perceived by our sensory system from the physical world, all right? And the result of representation of knowledge with the use of human language text. Everyone know what is a text when you write the report. When you buy a book. When you go to the library to read the journal, article, whatever. So all are text, all right? So text in conceptual world, because based on our study, we define all the text consists of conceptual world, right? So text in conceptual enable us to reconstruct the knowledge in the physical world. It's like when you read the book, then in your mind, basically you can reconstruct the meaning, and visualize the meaning, in the physical world. So that is a mental process, right? So without the text, it's impossible for us to transfer knowledge. It's not possible for you to reconstruct the knowledge by reading text, right? So this is a very, very important aspect or nature of a human language. So therefore, as an engineer, you must be professional with the use of human language, which include natural language, programming language, and the technical language. Technical language here means mathematics, right? So then why human language are so important? Just now I already mentioned description of knowledge, are basically based on the use of language, that is the nature of human intelligence for us, Whatever we discover, whatever we invent, we always write our invention, write our discovery in the form of a paper, report, books, article, etc. Then all these are basically the carrier of text, because inside the book, we have a text. Inside the paper, we have a text. Inside the report, we have a text. Inside the article, we have a text, etc. All right? And inside the library, basically, is full of a text, right? So This is for knowledge distribution. So it means the inventor or the pioneer who discovered the knowledge need to have a language to document, okay, their discovery, their invention. All right. After that, then we may have a new generation of people or student or scholar. They want to know what has been discovered by our pioneer, what has been invented by our ancestor, etc. Then how to know that? Answer is what? To read the text, then to understand the knowledge, okay, inside the text, right? So these are the two major activities, okay, with the use of human language. Then this slide basically first illustrate, right, for those pioneers who undertake knowledge discovery and product or machine invention, technology invention. So then you will see once they obtain the result, they want to use human language to document whatever they have discovered, whatever they have invented, right? So then the result will be the text, and all these texts will be stored inside the library. This is why every country, every city, every university has a big library. Now you understand, all right? Okay. And then how to describe knowledge. So basically, first we must have a data. So this is why we have an eye, we have a ear, we have five, like these five major sensory systems, which can transform signal into meaningful data. Then from a meaningful data into meaningful symbol in human language. So these are the two major steps. First, use a sensory system to sense, cognize, recognize, and knowledge. All right. So basically, is to transform signal into meaningful data. Then, from meaningful data, we need to transform them first into meaningful symbol, and this symbol could be word, faces, sentences. Okay, and then there are the basic element inside the text. So these are the two major steps involved. Then you will see the long-lasting problem faced by AI is the second step. Okay, so that is the big problem of symbol grounding. If we make a breakthrough, okay, in the second step, then you see this is a tremendous progress in AI. All right, so now you understand, and how come we can make such a breakthrough, right? Because we look at the fuzzy logic or fuzziness from a different angle, then suddenly, okay, then we realize, all right, so human intelligence leverage on fuzziness, okay, to achieve this transformation from meaningful signal into meaningful symbol. That's it, right? So then you see teaching could be also a very important process of research, because with teaching, we can also discover, okay, very important knowledge or theory, etc. All right, so this is the typical example, okay? Then how to understand the knowledge? For example, we have a pioneer, person A, they are the pioneer who have, discover new knowledge, who have invent a new technology, then they describe their new invention, new discovery in the form of a text. Then we have a younger generation of a scholar, student, professor, whatever, right, or engineer, etc. Then they want to know, okay, what has been discovered, what has been invented, right? So this is a Newton's statement, standing on the shoulder of a giant. Now you understand this sentence. Who are the giant in this case? Person A are the giant because they have already done the discovery, invention. Then person B or machine C are the newcomer. Okay, so their first job is to stand in on the shoulder of this giant person A, all right? So then they try to understand, okay, what has been discovered, what has been invented by the giant, all right? So then the process involved to decode, that means to transform the text back to the physical meaning in the physical world. And eventually we can simulate the meaning. It's like our imagination. It's when you read the report inside your mind, you can reconstruct a virtual version of the physical world. All right, so it's quite straightforward. So therefore, the process of knowledge understanding involved, okay, to transform a meaningful symbol back to meaningful sensory data. All right, then after that, then we can simulate the meaningful sensory data in the virtual version of the physical world, because the virtual environment is a virtual version of the physical world. All right, so we can say it's a digital twin of the physical world. Okay, virtual environment is the digital twin of the physical world. It's the same meaning. All right, so these are the two major steps involved. And today, I guess the conversion from text to meaning is not the big issue, right? As long as we know how to do the transformation from a meaningful signal into meaningful symbol. If that problem has been solved, then the reverse transformation should be quite straightforward, because they can make use of the same database or relational database. Then they know the bidirectional mapping. All right, if the mapping from a meaningful signal to meaningful symbol is not there, then there's no way for you to do inverse mapping or inverse transformation. All right, so this problem is go hand in hand with the simple grounding problem. All right, okay. So then of course, there are some challenges still faced. All knowledge in the physical world are crisp, but not all knowledge in conceptual world are crisp. But however, this is the advantage, as I mentioned, because we can do knowledge compression. Then with our small brain or small mind, we can store eventually large quantity of knowledge from the huge physical world or huge universe, right? So this is an advantage, right? So therefore, then people may want to know how do we construct CRISPR knowledge in the physical world from non-CRISPR knowledge in conceptual world. Then the answer remains on this symbol grounding function. If we have the symbol grounding function, then we can do the bidirectional transformation. And also the study in fuzziness or fuzzy logic, okay, will also help us to do this defuzzification, because later on you will see we have a process of fuzzification and also the process of defuzzification, right? So defuzzification is to transform meaningful symbol, okay, into meaningful or CRISPR data, sensory data, because we want to, when we take action, the action is CRISPR. You cannot take a fuzzy action. I want to do it, I may not want to do it. Then you hesitate. Once you hesitate, that means you do nothing. All right. So once the final output should be CRISPR action. All right. I do this, do that, do that. That's it. All right. But before you come out the CRISPR action, but you can play with the fuzzy rule, etc. Then combine them, etc. Then come out the final CRISPR decision, final CRISPR action. All right, so later on we will study this process and then give you some basic knowledge to cope with such a problem. All right, so then this summarize. So actually, the sensory system of a human being could output accurate data to a certain extent. Okay, not full detail. It's like when we enter the room is warm. All right, so the temperature is warm, is quite accurate, okay? To a certain extent, it's accurate, warm, nothing wrong, but then you can say we are not able to tell whether it's 30 degree or 32 degree, but we do not need to know this information. But remember, this is the advantage because we do the knowledge compression. Okay, there's no need for us to have symbolic representation for 30 degree, another symbolic representation for 31 degree, another symbolic representation for 32 degree. Otherwise, our mind will explore. Okay, we cannot store so many details. All right, and in particular, these details are not important to us. So that is the property, the nature of a human intelligence. So this is why we must let machine, intelligent machine, to imitate human-like intelligence. All right? Okay. So let's hear some example. We can say based on some sensory data, a car is moving. So this is not vague, John. Car is moving means what? The car is not at the rest. You should not interpret this like the car is at the rest. All right. Once you hear a car is moving, automatically say you exclude this case of a car is stationary. All right. A car is following another car. This is not vague. That means at least two cars involved. It tells you a lot of information or not very clearly. All right. But we do not know how close it is. Okay, what is the distance between them? All right, at what speed, of course, because for human intelligence, we do not need to know this information. No need to know this detail. Okay, because intentionally we compress knowledge. All right, then we have a concise version of knowledge, which should be good enough for us to reconstruct meaning in the physical world. So that is the magic of human intelligence. A car stopped at the junction. This is not vague, John. A car is not moving at the junction. You should not interpret it as a car is moving at the junction. Right? No such thing. Right? So there is a pedestrian. So this also is not vague, but of course we do not know what is the gender of the pedestrian, what is the height of the pedestrian, what is the color of the pedestrian, etc. Okay, so of course there's lack of certain precision, etc. Right? Like for human beings, sensory system intentionally avoid obtaining CRISPR data. So this is what I'm saying, because we need to do knowledge compression, because our mind is small, the universe, the world is huge, right? It's like our eye, John. Our small eye can perceive a large space because of focusing of the incoming light ray. So it's kind of a compression, John. We focus the incoming light into a smaller area, right? But without losing the detail. Then similarly with our sensory system, okay, and with the use of language, we also do a kind of knowledge compression, but without the loss of essential detail, right? So, and here I just show you two more examples. Like a car is moving very fast, okay, then you should not interpret it as a car is moving very slow. Okay, so there's no vagueness at all, right? A car is following another car closely. Then you should not say a car following another car and their distance is 1 kilometer apart. Okay, so that car is beautiful and large, right? And this car is powerful. So it tells you information. It's a very clear description. That truck is heavily loaded. That car is very noisy. The street is very cloudy. The street light is too dim. So you see, all these statements are fuzzy. It's intended because intentionally eliminate some detail, but it's not vague, right? Because vagueness will lead you to meaningless interpretation, right? Because when we say your report, your writing, or your book is too vague without the detail, we cannot understand what you are talking about. So in layman term, we should the term vagueness means this, okay? Lack of information, okay? No information or not enough information, all right? But all these statements you see is very clear. People understand, all right? So, okay. So then this is a question for you to think, is fuzziness about the belief or vagueness? So my answer is fuzziness is about the belief, all right? So it's like randomness is about the competition, compete for occurrence, all right? And the fuzziness is about the belief. So it means the CRISPR sensory data will trigger, okay, a set of a belief with a different level of possibility. Okay, some data will trigger the belief with a high level possibility. For example, inside the room, if the room temperature is 40 degrees, I guess that the possibility for you to believe that the room is warm should be 100%. 100% means what? Almost if you ask 100 people to enter this room, all of them will say this room is warm, all right? So possibility is very high. That means possibility for other people to generate the same belief will be very, very high, almost 100%. That means inside the room of a 40 degree, I guess everyone will say this room is warm, yes or no, all right? And there's no vagueness, John. You cannot say, I enter a room of a 40 degree. It's too vague for me to say whether it's warm or not. How can you say that? Once you enter, it's very clear, warm, finish, all right? There's no vagueness at all, yes or no, all right? So fuzziness is about the belief, okay? This belief is triggered by sensory data. So it's very, very interesting phenomenon for us to study. So now you see this lecture basically introduces the fuzziness, okay, from a totally different angle, all right? So you can do a comparison with the existing textbook in the library, in the internet. Then you tell me like if you could find a similar statement or similar description, then you let me know, all right? So then we can make these important remarks. The sensory system of a human being could not output crisp data. It is true, John. The sensory system of a human being output sensory belief. That is very important. It's like when you enter the room with a temperature of 40 degrees, instantly our skin will trigger our mind to say that this room is warm, right? Because when you say this room is warm, it's a belief, John. You believe it's warm. With the possibility, if the possibility is 100%, it means anybody enter this room will have the same belief like me. That means you are 100% certain, okay? Everyone enter a room with a 40 degree, will say, this room is warm, 100%, right? So, okay. But however, if let's say you enter a room of 27 degree, then you cannot say 100% certain that everyone enter the same room will say that this room is warm. Maybe some people may say 27 is cool, it's good, all right? So you see, okay, so when the sensory data are different, then the level of belief will be different. Let me use a possibility, okay? What is the possibility for the sensory data to trigger such a belief, all right? So it's quite important. And the most importantly, you see human beings are very skillful with the use of a sensory belief in order to determine crisp action. For example, when we drive our car, all right? Normally, we do not know, okay? What is the steering angle, how far away is our car with respect to the landmark at the left-hand side, right-hand side. I guess nobody knows, okay? We roughly, we are very close, we are near. Then based on that, we can determine crisp action. That means steer the angle. When we take action, action is crisp. It's not vague, John. Either you you steer toward the left-hand side or the right-hand side. There's no ambiguity at all. All right. So action taken by us is crisp. All right. So this is a very, very important observation. All right. And also, human beings are skillful with the use of a sensory belief in order to discover knowledge. So that is easier to understand. So you see, you may say, okay, at this point, this is more or less like a white color. This is at a certain level, you can say this is a white color. And then you may say this is a red color, like red color. And maybe this is a gray color or something like that. Okay, then these are the pedestrian, this is a passenger car, this is like a lorry, this is an office building, whatever, you see. So based on the visual signal, you will trigger all these belief, right, with a certain level of possibility for others to produce a similar belief or same belief, right? So belief basically specific knowledge. For example, the sky is blue. Okay, the sky is blue with a certain level of possibility, right? It is very possible. Okay, and then this looks like it's a cloud in the sky. All right. Then this is a taxi. This is a lorry. This is a tree, a green tree. Then this is the road surface. This is a landmark, etc. So it's a specific knowledge, okay, in terms of property constraint and the behavior, which is associated with the sensory data. The sensory data will trigger such a belief, right? So such association is one-to-many association. This is aspect of knowledge compression. So that means this is blue. I'm also believe this is also blue. So I just use a meaningful symbol blue to represent all these data which will trigger the same belief, of course, with a different level of possibility. That should be okay. So that means one belief could be triggered by a set of data. So therefore, then we have this mathematical concept of belief set, right? So, and one belief may correspond to a set of essentially data, right? So it makes sense, you know. And then you may say, if you use a camera to measure, actually the RGB value at a different point should be different, not the same, all right? Then we believe the raw surface is a dark color. You see, dark color is just single belief. Then it corresponds a set of value already, all right? So then here's an example. Let's say a man is tall man, is a belief, right? And the tall man may refer to a man with a height of 1.8 meter, 1.85 meter, 1.9 meter. So this shows you one-to-many transformation, all right? So one belief may correspond to a set of sensory data, all right? So this is a belief, this is a sensory data. So actually, this is an advantage for human intelligence to do knowledge compression. Okay, then in this way, our small mind, our small brain could store large quantity of knowledge from the huge physical world, from the huge universe. Magic, all right? So this should be the motivation behind human intelligence with the use of the phenomenon of fuzziness, all right? In order to transform meaningful symbol into meaningful data into meaningful symbol. All right, so that is important discovery. All right, okay. So then, since one belief may correspond to a set of sensory data, then we can talk about the belief set. Then it's quite straightforward. Then you see all the sensory data which could trigger a same belief with different level of possibility then consists of a belief set. Okay, so one belief corresponds to one set of data. For example, we may have a set of data about the temperature. Here is the temperature, for example, from 0 degree all the way to 100 degree. Then the same set of data will trigger three beliefs. Okay, the temperature is cool or cold. Temperature is normal, temperature is hot. But pay attention. So it's the same set of data. In this case, will trigger three beliefs, or each belief could be supported by a set of sensory data. For example, then beyond, but here you should not consider, let's say, possibility is 0, then you ignore it. You should not. That means possibility for you or for the temperature 60 degrees to trigger the belief of being cold is 0. Possibility for 90 degrees to trigger the belief of being cold is 0. So actually you must visualize this possibility distribution function. Okay, it's like one switch here, then all the way cover the entire range of the data. Must visualize in this way. Don't say that this belief only valid within this interval of sensory data. Wrong. Okay, so this belief is valid within the entire sensory data of a single sensor, right? For this sensor, right? Then for this one, this is the belief possibility distribution function, which start from here, 0, 0, 0, then start to go up, then go down, then 0, 0, 0. Then for this one, also cover entire range of sensory data, okay? From 0 all the way to here, then the possibilities start to increase until you will reach this 100%, okay? Then slowly it will reduce, because this once go higher, it may trigger another belief, very hot. Because hot, very hot are two different beliefs, understand? All right, okay. And this is a belief about the quality, low quality, medium quality, high quality, based on the measurement of failure rate. or reliability measurement. For example, if you sell 1 million product, then there's only 5 has a return for repair. Then the reliability should be let's say 1 million minus 5 divided by 1 million. It's a very high channel. All right. So from here you see, if the reliability is more than 80%, then quality is higher. And if reliability is between, let's say 25%, 80%, then you say median, all right? If the reliability is below 20%, 20% means about 80% of a sold item will come back for repair. Then it's a big headache to the company a lot, right? Because 80% of the product will return back for repair. Okay, so it's a problem, right? So then low quality, all right? So these are the belief with the same set of data. Okay, you may have a single belief, 2, 3, multi-belief, does not matter, right? So understand, so this is the belief set is quite important, right? Then here, just show you one more example. Like I said, from this picture, sensory data 25500 will trigger belief of seeing red color. Similar 25510 will trigger the belief of seeing a red color, and the 25511 also will trigger the belief of seeing red color. It makes sense, John. So actually, if you pinpoint anywhere, actually the RGB value will vary quite a lot, but the belief is the same. These are the red color, right? Okay. Then next question is how to measure possibility for a sensory data to trigger belief. So in one of the previous lecture slide, we have already mentioned. So the 3 popular functions are normalized Gaussian function, trapezoid function, and triangle possibility function. So we just use these 3 or combination of these 3 or one of these 3. It's up to you. All right. So it depends on the nature of the data, right? And also the experience of a human expert, because this is the way for us to transfer humans' experience producing or trigger such belief into machine. So let machine to have a similar behavior of belief, okay, based on the sensory data. So that is an important aspect of application. That means we transfer our experience, our knowledge, or our mental behavior into machine. Let machine just follow our mental behavior. That's it, right? Okay. So the answer to this one is to use a possibility function such as a normalized Gaussian possibility function, trapezoid possibility function, triangle possibility function. Then what is a possibility function? Basically, it's any function which takes value between 0 and 1. That's it. And the such value indicates a possibility for sensory data to trigger a belief about the specific knowledge, right? For example, you say you may be looks like it's a donkey, this is a dog, this is a cow, this is a cow, with a certain level of belief, right? And this is a boy, okay, this is a duck, okay, whatever. And these are the tree, and the sky's color in this area is blue, okay, you believe, and the color here is green, etc., with a certain level of belief, right? So, for example, this area is green, okay, high level belief, high level possibility. And then if you say these are the green color, then the level of the possibility should be lower, right? Because you see, its brightness is close to become a white color, right? So then these are the white color, okay? And the possibility level should be high, okay? So then how to represent the belief set, right? So let's say we give you a set of n CRISPR sensory data. That means xi is i's sensory data, right? Then possibility value associated to this xi for it to trigger a belief. This could be red color, green color, whatever. So just belief is any belief, right? So use this, okay? So then we use this symbol or notation to represent the possibility value. Therefore, then we can, for this belief, so this can represent a warm, hot, normal, good, whatever. Okay, kinds of belief. Okay, then we form the set. So you see, we have a sensory data. Okay, which will trigger this belief with this level of possibility. All right, and this possibility could be interpreted as a possibility for others to produce the same belief. Okay, what is the because it's you believe this is red color. Then what will be the possibility for others to also believe this is a red color? Okay, if it's 100%, that means for sure all the people when they see this color will automatically come out the belief of seeing a red color. That's it. All right. So you interpret in this way. Okay. So then again, you see this is the belief with a certain level of possibility for others to to have a similar belief. All right. So then how to determine this value? Just now I already mentioned, use a normalized Gaussian function, trapezoidal function, or triangle function. Right. Example, we have three beliefs about the speed. Okay, and these beliefs are slow, average, and fast. Okay, then for a set of sensory data vary from 0 km/h all the way to 220 km/h. Then we will see, okay, for this range of sensory data, how you will trigger the belief of slow. Then obviously above, you see above 100 km/h, then all the data will have a zero chance or zero possibility for people to believe that this vehicle is moving slowly, right? So moving slow will have a high possibility when the velocity is below, for example, 50 km/h. Then, okay, then for average speed, so you see actually it covers the entire range of sensory data, right? So if the velocity vary within this interval, then people will believe, okay, with a high level of possibility to believe that the vehicle speed is average. And if it's above 160 km/h, then automatically, okay, the possibility for everyone to believe that this car is very fast should be almost 100%. All right. So this representation, then actually this basically encode or represent the experience of a human, but don't treat this as a mathematic result. This is just a human experience. You are put yourself as a designer. You are totally free to design the belief function. All right. So that is a transfer of your knowledge. Okay. If you are expert, then you dictate. You say, must follow this way based on my experience, for example, it's like this. So this is the expert's experience. So now you see this is use this to describe experience of a human expert, then transfer the experience to machine, from human to machine. Think this way. This is not the mathematical proof or mathematical conclusion that you cannot change. I must follow this. No, this is just for illustration. All right. So you understand the principle. Okay. Then if you are expert, then you come out with your design solution. If you are not, then you approach an expert who knows, who have such experience, then let the human expert to help you to draw this possibility distribution. Okay. So this we just consider is a possibility distribution. All right. Okay. And one more example. Okay. So then what are the three beliefs if the speech sensory data is 40, 80, 120, 140, 180, 222. All right. Then for each belief set, okay, because each belief set, let's say we just look at this set of sensory data, right? Because each sensory data will trigger these three beliefs, because these three beliefs are related to the same sensory data. So each sensory data will trigger these all the belief, but with a different level of possibility. So this example is showing you about this result. Okay, it's also quite important. For example, 40 km/h will have 100% possibility to trigger this belief, slow motion. Then if your car travel at 80 km/h, then the belief of a slow motion, the possibility for people to believe that the vehicle is moving slowly should not be 100%, it's 50%. So you see like 50%, all right? If the car speed is go beyond, okay, 120, I guess it's zero possibility for anybody to believe that your car is moving at a slow speed. Nobody will believe, right? Like here, 0, 0, 0 means that nobody will believe, right? For normal velocity, if you travel at this slow speed, nobody will believe that your car moving at a normal speed, 0, right? Then in between, then you see if your car move at this velocity, I guess all people will say your car moving at the normal speed on the highway with the speed limit of 130 degrees, for example, right? So in Europe, it's like that. The speed limit, I guess, 120 or 130. In Germany, there's no limit at all, right? So, but in Singapore, it's 90, okay? So this depends on the country, context, all right? Then if it's go beyond 180, then nobody will believe that your car is moving at the normal speed, etc. Then fast speed, let's say at this velocity, no people will believe you are moving very fast, right? Even at this velocity, no people will believe you are driving very, very fast. It's slowly above 140, then people will believe really your car is moving fast, all right? So this is to help you to understand what is a belief set, all right? And since with a set of sensory data from the same sensor, we may have multiple belief. Therefore, we can talk about the combination of this belief. Then if we have more than 2 sets, then we can talk about the intersection between these 2 sets, union between these 2 sets, negation or complement of the set, etc. So actually, this is just for you to know, like in case for advanced decision making, which will make use of a combination of the belief, right? So then you just apply this formula. So it's quite straightforward, okay? So intersection is a multiplication of these 2 beliefs, but with the possibility function. So basically it means max operation, okay? So minimum operations, because this is the intersection, okay? So then you just compute. So you have this possibility distribution for belief slow, possibility distribution for the belief normal. Then we just compute the mean, okay, of these 2 distribution. Then this is the mean, right? Okay. Then disjunction means union between possibility function. Union means max operation, right? So then we have a belief, slow belief of a normal, and we compute the max, okay, of both. So it's a max operation. And for complement or negation of the belief, so mathematically, it's just to calculate 1 minus, right? So here we are showing you presentation of the fast, okay? So you see, this is the boundary, okay? Beyond this is being fast. Then, okay, before it is not being fast, right? So then in this interval, in this range of sensory data, we just compute the max. So it's not is this area. The reason the not, then we calculate max. Okay, so then this gives you the distribution, possibility distribution for negation of being fast. All right. Okay, so that's about the belief set. Then I believe is because of the existence of a belief set, then we have this fuzzy set, because fuzzy set is by doing fuzzification. Because once we have a crisp sensory data, we need to fuzzify it. For example, in this case, if the velocity of the car is 140 km/h, right? Then this crisp data will trigger all these 3 beliefs, because all these 3 beliefs by default, normally it covers the entire range of sensory data. Also, let's say in this area you have a 0, 0, then you should not consider they do not exist, right? 0, 0 means it covers entire in a range with a certain interval with a 0 possibility value, right? So like that. So it means with any sensory data, if you have a 3 belief, you will trigger all these 3 belief. Then it means what? With one sensory data, you have a set of belief. So that is a fuzzy set, right? Because the belief has a certain level of possibility, all right? So it's not the crisp set or normal set, all right? So then you need to know a little bit the history about the discovery of a fuzzy set, invention of a fuzzy set. So this is commonly recognized that the fuzzy set theory was introduced by Professor Lofty Zadeh, okay, in 1965, all right? However, before him, there are other scientists who have done some research work about the infinite value in the logic or logic with infinite number of value, okay, compared to the logic with a 2 binary number 0, 1. Then this corresponds to the logic with a value which vary between 0 and 1, all right? And I believe, okay, during the discovery or description of fuzzy set theory, they do not give a strong motivation about the usefulness, and they do not link this theoretical study with human intelligence or the property of the human intelligence. So this is why this theory was not recognized in the Western country. And it is in Japan, okay, we see the application and the successful application developed in Japan slowly make people to have a growing interest on fuzzy logic, all right? So this is the story. And this history again prove that the causality behind the fuzzy set theory or fuzzy logic should not be the study of vagueness, all right? Should not be the study of logic with infinite number of value, okay, between 0, 1. It should be the study about the transformation from meaningful sensory data into meaningful symbol in human language, all right? Then there's a requirement of doing knowledge compression. And in order to have this advantage of adaptation to valuation of sensory data, okay? And such adaptation is the advantage of human intelligence, right? So if we give this causality, give this kinds of motivation, I believe more people will accept, okay, fuzzy logic or fuzzy set theory, all right? So this is just for you to know the history about the discovery or invention of a fuzzy set, all right? And the application of the fuzzy set, okay, could be found in these 2 areas. One is for achieving human-like decision making. Another one is for achieving human-like action taken, right? And the popular one should be a fuzzy controller. So fuzzy controller basically is to imitate human-like action taken, right? Then for human-like decision making, then you will see in general there are 3 steps. First step is to transform crisp sensory data into fuzzy sensory data or fuzzy set. Then apply fuzzy rule to determine fuzzy decision. Then lastly is to transform a fuzzy decision into crisp decision. You see, so we fuzzify, then we defuzzify or defuzzification, all right? So then for the imitation of a human-like action taken, you see the process is very much similar, right? First step is to transform a crisp sensory data into fuzzy sensory data or fuzzy set. Then apply the fuzzy rule to determine fuzzy action. Then lastly is to transform a fuzzy action into crisp action. So this is a typical example when we drive our car. Actually, our brain undertaken the action taken. Then the action by our arm, by our hand are crisp. It's not fuzzy, it's not vague at all right? But Okay, the inner process involve falsification and fuzzy inference and the defalsification, but the output is a CRISPR action or CRISPR decision, right? So then you may want, what is a fuzzy set and what is the difference between fuzzy set and the belief set? Actually, they are not the same, all right? So without the knowing belief set, it's difficult for you to understand what is a fuzzy set, all right? So fuzzy set in this case, for example, if the input temperature is 50 degrees, for example, Fahrenheit, okay? Then in this case, then this will trigger one belief, second belief, third belief. So you have a set of 3 beliefs, right? Then possibility for this belief is 0. Possibility for this belief is, let's say this one, more or less 30%, right? Then possibility for this belief being hot is also 0. Now you see, it is a set with 3 entry. So you see the fuzzy set is not like a belief set, and the fuzzy set make use of the belief set, okay? So without the understanding the belief set, it is difficult for you to understand the fuzzy set, all right? So this join also help you to understand for each CRISPR sensory data, actually we can produce one fuzzy set, which correspond to this CRISPR sensory data, right? For example, quality control, if they say reliability of one type of a product produced by your company, for example, is 70%, then this will trigger this fuzzy set. Inside, we have a low quality, medium quality, high quality. Then if it is the reliability is 70%, then the belief of being low quality should be 0, right? And the belief of medium quality should be, if let's say you go up, then more or less like 50%. If let's say I choose this one as an example, let's say reliability is more or less about 74%. Then 74% will trigger, will include this entry inside the fuzzy set, medium quality with the possibility value 25%, high quality with a possibility value of 67%, and low quality with possibility value of 0%. Right. So now you understand this is the way to produce or transform CRISPR data into fuzzy set. Right. Then here I'm going to show you more example. For example, a car speed is measured to be 140 km/h. So this is a CRISPR sensory data. Then person A may say, okay, I'm 60% certain that the car is moving at the normal speed. Person B may say, I'm 90% certain that the car is moving quite fast. So you see, so you have 2 beliefs, normal speed and the fast speed with a different level of possibility, right? If there's another car is reduced to the speed of 50 km/h, then person C may say, I'm 40% certain that the car is moving slowly, and the person D says, I'm 70% certain that the car is moving at the normal speed. So you see, you have another fuzzy set, okay? And inside you have all the belief with a different level of possibility value, all right? So then how to represent the fuzzy set, okay? So give you, because for each sensor, okay, so we have a set of sensory data. It could be discrete value or continuous value, does not matter. Then here I use a discrete value to illustrate the idea, the concept, all right? Then within the range of this sensory data, eventually we may have M belief, right? Or 1, 2, 3, 4, 5, whatever, all right? So then these are the meaningful symbol in human language. Actually, this correspond, all right? Meaningful symbol in human language. So we have M for each sensory data, sensory data, each set of sensory data which correspond to one type of a sensor, such as temperature, pressure, velocity, position, whatever. All right. So then we have belief. Okay. So that means we have a set of M belief. So J equal to 1, 2, 3, N. All right. Then for each, okay, each sensory data, it will support or trigger this belief. Let's say XI. So any sensory data may trigger any belief. Okay, keep this in mind, otherwise you will get lost. All right. So any sensory data may trigger any belief associated with the same sensor. All right, but with a different level of a possibility, and some possibility could be zero. Right, only few sub-interval or short sub-interval will give some non-zero value, okay, or the rest get a zero, but it doesn't matter, right? Zero is also a value, right? So that means any sensory data will trigger this belief with this level of possibility. Now, let's say we give you I sensory data. Now it's xi. Then this one will also trigger all the belief G. Now you see the fuzzy set, the size of fuzzy set is equal to the number of belief. Then the size of this one is not equal to the number of believers, more than that. So this looks like a matrix genre. So now you see the difference between belief set and the fuzzy set. Okay, so the size of a fuzzy set is equal to the number of the believer, right? So then for this CRISPR value to trigger this belief with this level of a possibility. So this is the interpretation, all right? Then how to determine the possibility value? The answer is the same. Like you use normalize the Gaussian function, trapezoid function, or triangle function, etc. Right? So here I just showing you some example for you to understand how to fill up fuzzy set. For example, this is a speed from your car, for example, okay? And the speed sensor telling you now your car is traveling at 45 kilometers per hour, right? Then what should be the fuzzy set correspond to this CRISPR data? So this is a way for you to fuzzify your sensory data, okay? This is the CRISPR output from your sensor. Then how to produce fuzzy set which correspond to this one. So you just draw this line, then immediately you know, okay, for this value to trigger this belief being slow is 20%. Then you have this entry, slow 20%. If you also trigger the belief of being median, then median entry and the 20%. If you also trigger the belief of being fast, then in this case, the possibility is zero, right? But you cannot say zero is not counted. It's no, zero is there, but it's zero. If you do not write here, absent does not mean zero, right? So try to be careful, all right? So inside the fuzzy set, all the belief must be present, all right? And if some belief has a zero possibility for others to believe, then you put the zero possibility, right? Even for you to believe, this means zero. The possibility is zero for you to believe that this output will trigger this belief, right? And you yourself will not believe, and the others may not believe as well, all right? So this is meaning. And one more example, this may correspond to the action taken, all right? So you remember we can fuzzify the sensory data, and also the action taken, we can fuzzify it. We have a fuzzy action. Then after that, we must transform a fuzzy action into CRISPR action, all right? So here may correspond to the steering angle. Let's say steering angle means zero, don't change, but with a certain level of a possibility. If they say the current deviation is zero, then don't change it at all, right? So if you change a little bit, it's also don't change, all right? So within this interval, and then possibility value will drop, all right? So this one means still toward the left-hand side with a small negative angle, then big negative angle, negative big angle, negative small angle, positive small angle, positive big angle. So this could correspond to the fuzzy action for steering, okay? Then if let's say for whatever reason, okay, if let's say we want to have a steering angle, positive steering angle of A divided by 2. So you see negative A, negative B, negative A, positive B, right? So if we have this action, then what should be the fuzzy set correspond to this action, right? So then this one may trigger this belief, okay? Negative big value, then possibility is zero, because, okay? This is a positive, it's not negative. Then negative small value. Okay, the possibility for you to believe this positive number to be a negative small number is 0. You see 0, right? Then the possibility for you to believe that this is a 0 steering angle is not 100%, 50%, and the positive small number is also 50%, and the positive big number 0%, because here it's not bigger than A. So then possibility should be 0 for you to believe that this is a big steering angle. Okay, so this is to help you to understand how to produce fuzzy set from CRISPR data. So here is one more example. Okay, and here is the students' self-study time per day, right? Then we have 3 types of student: motivation low, motivation medium, motivation high. These are 3 types of student. All right. Now we observe that the one student, okay, today spent 40 minutes to do self-study. Then what should be the fuzzy set? Okay, so fuzzy set will contain all these beliefs. Okay, and the possibility for you to believe that this student's motivation is low should be 0, right? Because this student has spent this amount of time to do self-study. Then possibility for you to believe that this student has a medium motivation, then is 50%. And the possibility for you to believe that this student has a higher motivation, then is equal to 50%. All right. So then you see, this is the way to produce a fuzzy set. All right. And then here I'm going to show you example of imitating human-like decision-making in restaurant. Then subsequently, our major focus is on feedback control, because when we design engineering sensor on the engineering context, okay, majority application is feedback control, right? Then we'll talk about the fuzzy sensor, fuzzy controller, right? So before we enter the study of the next section, so I just use this simple example to illustrate how to make a machine to imitate human-like decision-making. For example, you go to a restaurant to take your dinner or lunch, all right? And then you want to pay a tip to the waiter, all right? Then you will take 2 input and produce 1 decision, 1 output, right? 1 input is food quality, another input is service quality, all right? And you can do evaluation based on within the scale of 0 to 10, all right? Based on your experience, because assume you are expert, okay, in taking dinner or lunch in restaurant. So roughly you have an idea whether the food is good or the service is good or not. So before you do the classification, you just rank, okay, scale from 0 to 10. Eventually you may say the food quality is a 6 and the service quality is 8, something like that, right? So that is a CRISPR data. So you get evaluation of the food quality, get evaluation of service quality. That is a CRISPR data. Okay. Then after that, you must classify both evaluation. So then you use this possibility distribution function. Okay. Let's say, and you want to have 3 belief for, okay. Evaluation means it's a sensory data. Okay. So it's CRISPR data. Then within this range of data, you come out the 3 belief. 1 is bad, so food quality is bad, food quality is decent, food quality is great. Service, you say poor service, acceptable service, amazing service, right? So you from the set of evaluation, you come out that there's a 3 belief, right? Then each belief will have a probability distribution function. So we highlight with a blue color, green color, red color, okay, similarly. Then for decision making is the same, okay? So you will take 3 fuzzy decision. I will give a small amount of a tip, or medium amount of a tip, or a big amount of a tip, all right? Then for these 3 fuzzy decision, then you also have a possibility distribution function. Then you use different color, etc. Then you apply the fuzzy rule to do the fuzzy inference. You can say if the food quality is bad, okay, then tips may be 0, okay. or is the descent, and is how much, etc. So based on your experience, you establish the fuzzy inference rule. Then you come out the fuzzy decision, all right? Then after that, you defuzzify the decision. For example, your decision is one input telling you that you must give a median amount of tips, okay, with a certain level of possibility, all right? So this is one input tell you this, and another input telling you that I must give a big amount of tips with a certain level of possibility, right? Then you have a second fuzzy decision. Then you must combine these two together. Then there's a method for you to calculate the center of gravity of these two possibility distribution. Then use that one to determine the CRISP value, project that center onto this horizontal axis. Then you will get the value for the amount of dollar that you must give to the waiter, all right? So we will come back to the detail about this procedure in the next section, because the procedure are similar. So I'm not going to repeat the similar procedure for decision making. So let us focus on the study of imitating human-like action taken, right? Okay, so that is a fuzzy control. So in our real life, there are many real examples which make use of a fuzzy controller. For example, inside the car, you may have several fuzzy controller. For example, automatic gearbox, etc. is a typical example of a fuzzy controller. Then for rice cooker and the airflow control system or ventilation system in a large building or large factory, etc. So all these systems may need to have a control of the flow, control of the temperature, control of the timing, etc. Control of the steering angle, right? So we can use a fuzzy controller, right? So we can fuzzify sensory output, then make use of a fuzzy rule, then define the fuzzy action, then obtain the crisp action, right? So here you see this could be a typical example of a fuzzy action for the speed control, right? So the speed control could be stop the car for whatever reason, right? Or slowly drive the car, or drive the car at the cruising speed and drive the car fast, okay? Or drive the car very fast, all right? So for all because these are the fuzzy action, so you can at the cruising speed with a different level of possibility. So this is the action. It's possible for the car to take this action, all right? If the possibility is high, then more or less the action is driving at this speed. If the possibility is low, eventually it may cruising speed may reach this one, but with lower possibility. So this is why these are called the fuzzy action. So it's action we associated with the possibility of different level of possibility, right? So this help you to understand, okay, the meaning of the fuzziness. Fuzziness means any data, okay? It could be sensory data, decision, or action, okay? Or choose any data or any choose which are associated with possibility function, all right? So there's a possibility for a machine for us to take this action, to make this decision, right? Or to fuzzify or to transform the sensory data into a meaningful symbol in this way, or to this meaningful symbol, all right? Something like that, okay? Then what is the procedure of implementing fuzzy control? Then you will see this procedure are very much similar to this one, more or less the same, all right? So then here, once you see the detail, then you know the detail about this. This slide basically telling you a summary, that's it, all right? Then the detail will be similar, like the case of doing fuzzy control. So step number one is to transform a crisp sensory data into fuzzy condition. So you may have one sensor, two sensors, n sensor, okay? In the simple case, maybe single sensor, but this is a general case. We may have n sensor, n may be equal to 1 or 2 or 3, whatever, right? Then after fuzzification, what we have is the fuzzy set. Each set basically is a belief, is a set of a belief with a possibility function, right? Then we can, because for each belief inside the fuzzy set actually is a condition. We call them as a fuzzy condition. So they will serve as a condition. Then we apply the rule, okay, to transform fuzzy condition into fuzzy action or decision, okay? If it's imitating human-like decision, then it becomes a decision. If it is to imitate human-like action, then this is the action, right? So you see, this is we use rule to transform, right, the fuzzy condition into fuzzy action. Then after that, we will transform fuzzy action back to crisp action, all right? Because some fuzzy condition will trigger, okay, maybe a different type of action, okay? And each possible action will have a different value of a possibility. Then we just compute. It's like a computer weighted sum of all the fuzzy action. Then we get to the center, okay? Then project that on the horizontal axis. Then we get the crisp value as the output. That's it, all right? So now I'm going into the detail, okay, for each step. Then you will understand how to convert crisp sensory data into fuzzy condition. Answer is what? To use belief set, which include possibility function. For example, within this range of car's speed sensor, right? Then it will trigger 1, 2, 3, 4, 5 belief, right? Each belief has its own possibility distribution function, right? So this is the first one, second one, but always remember when we have a horizontal line which is 0, then you must consider it's there 0 there, right? Then this is another possibility distribution, okay? And the third one, fourth one, fifth one, that's it, all right? So then you may say, okay, how to draw this human experience, okay? So this is a result of a design based on human experience. That's it. There's no mathematics involved, okay? You should not say how to calculate this curve. No, this is just by human's experience. Then you must consider this is advantage because we can easily transfer our own experience into machine in this way. Okay, very simple way, John, all right? And one more example, right? If let's say we have a temperature sensor, which output data vary from 8 degree to 32 degree. Then within this range, we have a 1, 2, 3, 4, 5 belief. Then based on our own experience, then we come out the possibility distribution for each belief, right? Now you see this is advantage. This is the way we transfer our experience into machine. And the example is use a video signal sensor. And we also could transform image intensity into meaningful symbol. For example, these are the area correspond to dark area. Then this is a gray area with a certain level of belief. So that means this is a range of intensity. Assume each pixel encoded with 8 bit. The intensity will vary from the 0 to 255 channel, right? Then you remember we can also calculate the occurrence for each intensity level. Let's say for intensity equal to 0, the number of occurrence. Intensity 1, number of occurrence. Intensity, there's 100, number of occurrence. Then we brought out the occurrence number. So this occurrence number is called as a histogram, right? Then the peak value basically will give us a strong belief, right, that this pixel value correspond to gray color. And there's a value here. This gives us also, this peak value, strong belief that we have a dark color. And this peak value indicate that, okay, we have a bright color pixel, right? Something like that. Then use this histogram, eventually it can guide us to design this possibility function, right? So we use a histogram to make a design of possibility function. So that's the answer to the first question, how to transform CRISPR data into fuzzy set. Then next question is how to transform a fuzzy condition, because we treat the fuzzy set as a fuzzy condition because inside we have a belief. Then each belief is a condition. Okay, it is dark, it is gray, it is fast, it is cold, it is warm. These are the conditions. Okay, then how to transform a fuzzy condition into fuzzy action? Then we just apply rule, fuzzy rule based. Then again, this rule are designed based on human experience or human intelligence. So again, this is a way for us to transfer our expertise into machine. If let's say, usually we use this kinds of a formula. If fuzzy condition is true, then we take fuzzy action, right? And here is an example. If the speed of a car is too fast, then quickly increase the braking force. If the temperature in the room is too warm, quickly lower the value of a temperature setting. If the distance to a frontal vehicle is too far, quickly increase the speed of the flowing vehicle, right? Because we want to follow the front moving vehicle. If the distance is too large, then we must quickly catch up. Basically, these are the simple fuzzy decision rule. Then you see this rule describe human experience, all right, or common sense, all right. One more example, if a car is moving too close to the left landmark, then rotate the steering wheel clockwise. If a car is following a fast-moving car in front, then we must increase the safety distance. If both of you travel at high speed, then we must increase the safety distance. If the value is foggy, reduce the car speed, all right? If error signal is big, this is like inside the feedback control loop, okay? They increase the control signal, right? So if the payload is big, they increase the car's output power, right? So these are the rule-based fuzzy inference, which will transform a fuzzy condition into fuzzy action, all right? Here is one more. And for the last example, we will apply this rule. So this is an example coming from the design of automatic gearbox inside vehicle. For example, if a car's speed is extremely slow, then choose the speed gear ratio 1. So you see a lot of cars has automatic gearboxes. So they basically make use of this type of rule, right? If car speed is very slow, choose the speed gear ratio 2. If a car speed is slow, then choose the speed gear ratio 3. If car speed is normal, choose the speed gear ratio 4. If a car speed is fast, then choose the speed gear ratio 5, right? So these are the rule for fuzzy inference, right? Then how to represent the action? Because we know the fuzzy condition. Okay, we use sensory data to produce a fuzzy set, use that fuzzy set to serve as a fuzzy condition. Then based on our own experience, we can come out the rule for fuzzy inference. Then inside the rule of fuzzy inference, there's an action, because if condition, then action. Then how to represent fuzzy action? So we can use the same principle. That means for each action taken, then we associate a possibility function, right? For example, here's an example. Let's say we have 5 fuzzy action, action L1, L2, L3, L4, L5. Then for each action, we associate a possibility function, right? So normally in this case, we use a triangle function, okay, to represent possibility value, right? Let's say for this action, okay, so at this value output, and if let's say the possibility to take this action is 100%, then we will output this value, CRISPR value. If we are not certain whether to take this action or not, let's say 80% certain, 80%, okay, then it's better you choose this value or choose this value, okay, so something like that. If you have hesitation, okay, if let's say I'm only 20% certain I want to take this action, then you use this as an actual possibility distribution. So you cut off here. So this is why we associate a full scale possibility function to each possible action. This is a full scale. Then based on the decision rule, fuzzy decision rule, if this condition, then this action, because the condition has a possibility, because that possibility will transfer to the possibility of the action, okay? If the condition's possibility is low, then the action's possibility will also low, right? So it's like this, right? So, and once you have a fuzzy action, then how to transform fuzzy action into CRISPR action? Now you understand already, because eventually some belief will trigger action. fuzzy action with a non-zero possibility. Because there are many just trigger action with zero possibility, then ignore them, right? Only return those with a non-zero possibility value. Eventually maybe 2, 3, 4 example. Then for example here, you may have 3 fuzzy rule will trigger 3 fuzzy action. Then with a different level of a possibility. So these are the actual possibility distribution. Actual one means what? Use that possibility value to cut off, okay? Oh, because this is the full scale means only with the possibility of 100%, right? Then you have this triangle. If it's 60%, you must cut off here, okay? Then the below one is the actual one, all right? Let's say you have a one actual one, second actual one, third actual one. Then add them together, compute the center of gravity, project the center of gravity into the horizontal axis, put this CRISPR value. Then this will be the output value, all right? So this is the mathematics. And here I shall show you one example for you to understand the procedure. For example, condition X will trigger fuzzy action D with this level of a possibility. Condition Y will trigger action E with high level of possibility. Condition Z will trigger action F, very level of possibility. All right. Since these 3 conditions will trigger 3 non-zero possibility action, then we must consider them all together, put them together, then calculate center of gravity, then project the center of gravity onto the horizontal axis. So if let's say center of gravity is here, then this value is a CRISPR value will be the output. That's it, all right? Because this is the action with a specific value, all right? So here's one more example, okay? Let's say we have the fuzzy controller for the steering angle of your car. And within the range, let's say the steering angle can rotate between negative 30 degree and positive 30 degree. And within this range, we have 1, 2, 3, 4, 5, 6, 7 believe, all right? Then for each value, let's say you have a sensory input, this could be the distance, and based on the distance, then we make a decision whether we need to slow down the speed. This is based on the offset between our vehicle position with respect to the landmark towards the left-hand side, right-hand side. Then we will decide whether we rotate the steering angle with a big negative, a big value, negative small value, or 0 value, or positive big value, positive small value, or 0 value, etc. Right? So assuming in this situation, condition 1 will trigger action 1, condition 2 will trigger action 2, and the possibility for condition 1 is 80%. Okay, the possibility for us to take, or for the machine, the vehicle to take this action is 80%. Possibility for the vehicle to get 2 is 10%. Right? The actual possibility distribution for action 2, then this is the actual possibility distribution for action 1. Then put them together, then it's like this. Then we compute the center of gravity should be somewhere here. Then project it onto the horizontal axis. Then we get the negative 10 degree. Then this will be the output. Rotate the steering wheel or steering angle or the steering wheel, okay, by negative 9.3 degree, roughly negative 10 degree or something like that. Okay, so this will help you to understand the way transform fuzzy action into a single CRISPR action, right? So here I say, wow, all this. Actually, with the computer, it's not an issue. And application, really is only single condition, immediate condition, and so your trigger discrete output is not steering angle. You can rotate 9.31, 9.32, or something like that. It's a continuous. And in some application, you may have just a discrete action. Okay, and the typical example is this one. The action taken is because you only have a 5 gill ratio. You cannot say change the gill ratio to 3.1, 3.4, 3.6, 3.7. Because the legal does not support this continuous value. So you only have a few set of value. Then in this case, you will see the actual implementation will be extremely simple, all right? And these are the general principle for you to follow, all right? And then for specific case, then you must consider specific situation. For example, here we are going to design fuzzy controller for automatic gearbox, all right? Then what should be your design solution? So actually you can find out the detail in the previous slide, because in the previous slide, we have gone through some examples which are relevant basically to this question, all right? But here, assume we have already designed the belief set, the fuzzy set, etc. And then we know that the output action is only gear ratio 1, gear ratio 2, 3, 4, 5, etc. Right? And then we have the fuzzy rule, okay, for inference in the previous slide. Now, okay, we want to do a test. Okay, what happens if the velocity speed of the vehicle tell us that currently our car is driving at the 55 km/h? Then what should be the gears ratio? All right, 55 km/h basically means is this one. Then this CRISPR sensory data will trigger, in this case, very simple, trigger single believer, right? Because then you will trigger this believer, normal speed, okay, with this level of 60% of possibility, okay? So because the rest is 0, 0 is all are 0, so it's quite simple, okay? So answer is if the car speed is 55 km/h, the speed of the belief, okay, after falsification, the belief is just a single one. The speed is normal. Then we apply the rule. There's only one rule for us to apply. If the car speed is normal, then choose the speed gear ratio 4. Done already. So you see, so in many cases, you may encounter a simple situation, right? So you do not need to follow all this complicated calculation. But as an engineer, you should know, okay, the normal situation and the basic principle for you to handle all kinds of situation, right? Okay, so this example just showing you that in practice, it is quite simple for us to implement fuzzy controller, right? So that's all for the study about this lecture on fuzziness of measurement, all right? The key takeaway is for you to understand that it is interesting for us to transform engineering sensor into human-like sensor. Then in this way, we can implement human-like action taken, human-like decision taken, all right? Because human-like intelligence is quite impressive. If we can make future machine or future system or future product to imitate human-like intelligence, that should be a tremendous progress, all right? So then this lecture basically is a necessary step toward that direction, all right? And the key takeaway from this lecture also for you to understand what is the belief set, what is the fuzzy set, then how to undertake fuzzy control with CRISPR sensory data as an input and CRISPR action as an output, and what should be the inner process involved, and what should be the solution involved, etc. All right. So thank you for your attention, and I'm looking forward to seeing you in the study of next lecture.